In this section, we are going to generalize two concepts that we encountered at the very beginning of this course. Now, the first concept is that the notion of a normal vector to a plane is going to extend to the idea of orthogonal complements. The second concept is the notion of the projection of one vector onto another vector is going to extend to the concept of orthogonal projections onto a subspace. So the first concept that we are going to explore is the idea of orthogonal complements. Now, we already know that a normal vector, say vector n, to a plane is orthogonal to every vector on that plane. Now, if a plane passes through the origin, then it is a subspace, say W of R3, as in the span of the normal vector. So in other words, we have two subspaces of R3 with a property that every vector of one subspace is orthogonal to every vector of the other subspace. Now, this is the main idea behind the definition of an orthogonal complement. So let's take these ideas and define our formal definition. So here's our formal definition for an orthogonal complement. So we want to let W be a subspace of Rn. And we say that a vector V in Rn is orthogonal to subspace W if vector V is orthogonal to every vector in subspace W. Now, the set of all vectors that are orthogonal to subspace W is called the orthogonal complement of W. And we denote this as W raised to that perpendicular symbol, which we pronounce as W perp. Now, in set notation, we say that W perp is equal to the set of all vector V in Rn, such that the dot product of vector V with vector W is equal to 0 for every vector W in subspace W. So to better help us understand or interpret this definition, let's go ahead and think about the following illustration in space. So let's go ahead and let W be a plane passing through the origin in R3. And we also want to go ahead and let L be a line passing through the origin in R3 such that this line is normal to the plane. Then we can observe here that every vector V on the line is orthogonal to every vector W on the plane. Or in other words, we can say that the line L is equal to the orthogonal complement of the plane, or L is equal to W perp. An alternative way to think about this, we can say that the plane consists precisely of those vectors W that are orthogonal to every vector V on the line. And again, in other words, we can say that W is equal to L perp, that the subspace W is equal to the orthogonal complement of the line. Now, using this illustration, we can actually observe some pretty cool and interesting properties that occur with orthogonal complements. So the first property that we're observing here is that the orthogonal complement of a subspace turns out to be another subspace. And we can see this with the two conclusions above. We can see that the complement of the subspace W equals the subspace L, and that the complement of the subspace L is equal to subspace W. Another interesting property that we're observing here is that the complement of a subspace turns out to be the original subspace. Now, to better help us appreciate this second property that we're observing, let's start by thinking about how we know now that the complement of W is equal to subspace L. Now, if we take the complement of both sides of this equation and use the conclusions from our illustration up above, we observe that the complement of subspace W is equal to the complement of subspace L, which we know is equal to subspace W. So we can see here that the complement of a subspace equals the original subspace. And this doesn't just hold true for this case, this is going to hold true for the line as well. Now, what's even more fun is these properties that we're observing here hold true in general. So let's go ahead now and summarize the generalized properties for the orthogonal complement of a subspace. The following are some generalized properties of the orthogonal complement of a subspace. So to begin, we want to let W be a subspace of Rn. Now, the first property we observed with the previous illustration. And this first property tells us that the complement of a subspace is a subspace of Rn. The second property was also observed with our previous illustration. And the second property tells us that the complement of a subspace is equal to the original subspace. Now, the third property is telling us that the intersection of a subspace with the orthogonal complement of that subspace is equal to the zero vector. So in other words, this is letting us know that the zero vector is the only element in the intersection of a subspace with its orthogonal complement. And the fourth property, last but not least, tells us that if W is equal to the span of a set of vectors, say vector W sub 1 through vector W sub k, then vector V is in the orthogonal complement of subspace W if and only if the dot product of vector V with vector W sub I is equal to 0 for all I being equal to 1 through k. Now, with these four properties, we can now go ahead and express some fundamental relationships involving the subspaces associated with M by N matrices.